we're gonna talk, or we're gonna have a lot of talks from Sami and Hector. And because it's a combined session, we also have two speakers for the overview talks, Scott and Julia. So yeah, as we said, I give you a warning after 10 minutes and you have 12 minutes for the talks. Take it away.
Great, thank you. Yes, so I'm going to give you an overview of what Sami and Hector have been doing over the last year and also look ahead a little bit. But when I get to the Hector parts, Julia will step in and give you the rundown of where Hector is, which is pretty exciting actually. So stay tuned for that. What we will be doing is really taking you through a lot of science that we've been doing over the last year. But of course, there's a lot of other talks that will be happening straight after me. So I'll not cover everything, obviously, but just cover a few highlights that aren't already going to be covered a bit later. So as Lisa made the point before, there might be a few people who are new to Astro 3D. So just a minute to give you a brief intro to what SAMI is. SAMI was a project we started about a decade ago now, a little bit more than that. First to build and then to run a survey using a multi-object neutral field spectrograph called SAMI, developed jointly by Sydney and the AAO, as it was at the time. Really to drive the idea of doing large multiplex IFU surveys to be able to cover a large range of parameter space in terms of galaxies. Now, the survey completed its observations up at the AAT in 2018 with over 3,000 galaxies observed. But we continue to do an awful lot of really exciting science as part of the team, even though the data taking has been completed. SAMI this year, probably the biggest thing we've done is do a full data release, which is a huge amount of effort by a lot of people. I'll mention that in more detail in a few minutes. We also still managed to publish a lot of papers. Given COVID and all the other things that have been going on, I do take my hat off to the team for being so productive. We've published 15 papers so far this year, and we haven't finished the year yet. It's really fantastic to see so much productivity. We've managed to have a great SAMI science meeting. That was in July this year, obviously online. There's various things that have been worked on for Hector, obviously the build, and Julia will talk about that more a bit later, but also working on pipeline development, including getting ADAX funding that Nick Scott led. We've also got the first AAT time scheduled for Hector this semester. We should have actually already been on the telescope with Hector now. If it wasn't for the lockdowns, we would have been there. But also, I just make the point that we've had a lot of really great students come through and actually complete now. We've got other great students that are still going in SAMI, but we have had 4 PhD completions over the last probably 6 months or so. Tanya Baroni, Matt Varadale, Stefania Santi, and Simon Dealey all completed their PhDs in the last few months. So it's really been fantastic. So just mentioned data release 3 for SAMI. This was really a culmination of a huge amount of effort by a lot of people. What I've highlighted here are just the names of the key people who worked particularly on the data release. So big thank you to those people in particular, but also the rest of the team who spent also a lot of time looking at quality control and various other things. This data set is vast in terms of both its data quantity and the types of data we have. And it's all been released through Data Central, which has been fantastic. So what I'll do now is just take a few minutes to talk about a few science highlights. There isn't time to go into detail, so please look at the archive links if you want more detail. The first one I'll talk about is a paper submitted by Tanya Baroni, who working jointly at ANU, but also at Sydney, doing a comparison between the SAMI data that she'd previously worked on other papers from her thesis and LEGA-C, a higher redshift VMOS survey. This is a really interesting comparison between the stellar populations of these two different redshifts, and VMOS is obviously a much higher redshift. The data is very deep, which allows us to make these stellar population measurements. And interestingly, we do see essentially the same trends, particularly metallicity, that we see in the local universe. And particularly, the metallicity seems to depend mostly on mass divided by radius, or approximately potential. The other thing we found in SAMI at low redshift was that the stellar population ages. seem to depend mostly on mass over radius squared, that is essentially stellar density, surface density. But we don't see the same features at high redshift in the LEGA-C survey, which is probably driven by the fact that you're still seeing a buildup of the stellar populations over time at that epoch. I think a really intriguing result. Another nice bit of work, mostly based on stellar populations, is from a PhD student at Oxford, supervised by Roger Davies, one of our PIs at Oxford. Peter looked at the alpha abundance, so particularly, mostly this is magnesium, but sort of general alpha abundance, as a function of both environment and velocity dispersion of the galaxy. And this, again, is really enabled by the fact we have a broad range in mass and environment for these SAMI galaxies. There's a very well-known trend in alpha over Fe increasing to high velocity dispersion. What's less clear is whether there's a trend with environment. There's some nice work which McDermott did a few years ago, that was 3D. That showed there was a trend comparison between Virgo and non-Virgo results. But what Peter was able to show, and if you look at the diagram, see if you can see my cursor, the bottom one's a smooth version. The red is higher alpha over Fe, and obviously it increases with dispersion very strongly, but if you go vertically, is increasing density of environment, you do see a trend separately with both environment and dispersion. So this is implying that you have quicker truncation of star formation in these high density environments, which is physically what you'd expect. It's a really, really nice result. A paper I'll briefly mention that I published earlier this year is trying to understand the connection between dynamics of a galaxy and its quenching, and trying to see whether the difference we see between, in terms of kinematics, the spin of galaxies, when you look at breaking down by star formation rate, can be understood in terms of just a fading of a star forming disk that actually changes the observational kinematics. We did some very nice modeling, mostly thanks to Dan Taranu, who was in Perth, is now over in Princeton, and we were able to show that actually the big differences we found in spin between the SAMI galaxies that are passive and star forming, only a small fraction of that can actually be put down to disk fading. We also tried incorporating progenitor bias into that too, and it didn't really help. So we need intrinsic evolution of the kinematics in order to actually get the differences we see. So now, at this point, I'm going to just hand over to Julia, who can tell you a little bit more about Hector and where Hector is.
Sorry, it works better if I mute. The main point that I want to make in the first 3 slides is that Hector is here now. It's no longer something for the future we're talking about coming up. It's here right now. These first few slides to show you the real thing. These are all final pieces. These are all parts that are ready. They're sitting in the lab. They're ready to ship to the telescope. We had them in a truck in June to go to the telescope when the lockdown happened. We're ready to rock and roll, and it's really exciting. So what you've got here, can you actually see my mouse now? I've done a mouse takeover. I don't know if you can see it. No, you can't. Okay, it's not going to work. All right, no worries. We won't do that then. The top left picture is the robotic gantry and the field plate holder. This positions a series of very high precision magnets shown in the bottom left. The precision of these machining is something that we have never ever done before, down to 1 micron precision. This positioner is currently performing, it had to perform to position these within 10 microns for Hector. It's currently performing at only a few micron level, which is actually amazing to be able to put very strong 100 Newton magnetic forces at that sort of level. It's got a metrology system and these very, very precise pickup arms. Next slide, thanks, Scott. Sorry, right, there we go. On the left, you've got the new spectrograph. Hector uses 2 spectrographs, the existing A omega spectrograph and a new one called Spectre. The Spectre spectrograph is there in the big black box, ready to be installed up at site. On the top right, we've got the new field plate, which is sitting there on its mount, ready to be installed onto the top end. And when it's loaded with the sky fiber system shown on the bottom right, it will have a whole bunch of these subplates around the side, which will do sky fiber measurements in a different way to how they've been done before. In the middle, at the bottom, there is one of those subplates, and you can see little tiny dots towards the top of that image where you can see light coming through each of the ends of the pistons. The pistons on the bottom left have amazing precision on the inside of each of those pistons to get the angular and positional accuracy of miniature prisms onto fibers within incredible tolerance. Next slide, thanks, Scott. The main working part, if you like, of Hector that is new and innovative is really in the new hexabundles and in the new positioner. The positioner actually corrects for telecentricity on the telescope, which has never been done before. And rather than just putting down hexabundles on a flat plane, we are hovering them at a 3D sense above the field plate to correct for telecentricity. And that's never been done before. And that has an amazing amount of fun being able to design a system that does that. The top left picture shows all the guide bundles and their ferrules. That was just before shipping. The guide bundles have been shipped to site. In the center, the top, there is a picture of one of the hexabundles. I said, these are the real things. That's hexabundle letter J. It's actually going on sky. It's sitting in its rotation arrestor with its end cap on, which protects the prism. If you look to the bottom left, you can see one of those unclothed without its prism holder on it. Yep, that's the one. So showing these tiny little 3mm prisms. We glued them onto the hexabundle face shown in the middle there, which with 0.1 of a degree accuracy in all angles and micron precision. Being able to do that and the amount of new science and new instrument technology that went into just that last ½ centimetre of the end of that ferrule was quite incredible, but that's another whole talk. The remaining pictures here are showing the instrument packed up, ready to go. These new format bullets, we're doing bullets differently to how we've ever done before on telescope. That's really interesting too. I won't go into the details. We had to do these unique tiny splice boxes to protect the splices because of retrofitting to 2DF that we didn't have the space that we had in SAMI. They're all done. That's what that black box is on the bottom middle. It's all complete, showing the fiber cables all ready to go. And then this left of center, the bottom, is one of the bullets packed up with the sky fiber racks lined up in what we call the toaster rack. There's two of these bullets have the toaster racks, and it also has the hexabundles lined up under that cream colored box. It's all there, it's all packed, it's all finished, it's all ready to go. Just got to put the lid back on, right? So it's really exciting. Next slide, thanks, Scott. Okay, so the current status is that we should be installing on the AT right now as we speak, but we will do so as soon as the lockdown ends. We have 38 observing nights were awarded to the Hector Galaxy Survey in this semester. So 27 of those are with Hector and 11 of them are actually with 2DF to fill out the Hector input catalogue. And those ones are underway and those are going anyway because they're done remotely, so we don't need to have the instrument for that. But the Hector nights currently scheduled, second half of October, a couple of weeks at the start of December, and then in January. So we're starting off, so these plots show the sky regions that we will be covering. That we heavily overlap the waves north and south regions. So the top plot there shows the southern hemisphere regions, including the blue strip, which is waves south, and the black dots are the clusters, 12 clusters we'll be also looking at. So we're starting off with some 3 panels, if you like, out of that waves region shown in the plot below it in orange and in red. And that's what we're observing from the beginning of the survey. Once those regions are covered, we'll be filling in the bits in between those regions. And that's to stagger across RA to ensure that we can use all times of the year. And so right at the moment, we're chomping at the bit to get going. It's going to be very exciting over the next year as the data starts coming in. We've had, so far on this project, we've had 2 HDRs in Astro 3D who are just about to finish. That's Rebecca and Adeline. So they have been Hector higher degree students on working on the instrument. And so that's exciting, and they're both writing up now and finish in the next month or so. We are now starting the process, or we're halfway through the whole process of a new hire for Astro 3D Hector postdoc at USyd. So that'll hit the ground running right when the data does, which is very exciting. And there's been many Astro 3D people heading up science roles for Hector, and we can't do this without them. There's like these plots you're looking at here were put together by Sam, who's heading up the Tiger selection group. But there's a whole host of people, and I won't list them all off right now, that are part of Astro 3D that have significant roles in Hector, and those roles, of course, will have really good value in the years going forward. But I would like to point out, though, the unseen thank you that I'd like to put forward, and that is that the Hector instrument has been built by the Australis Instrumentation Consortium. We've got a tiny little logo at the top of the screen here. So the Australis Instrumentation Consortium between USID, Macquarie and ANU is Australia's leading astronomical instrumentation consortium. And this instrument has been headed up out of the USID node and with support from the Macquarie node. And within my Australis team, I've got 25 people who have been involved in various capacities in building this instrument. The science team gets this instrument that appears without ever meeting those 25 people, without ever seeing them. But I want to do a really big shout out to my fantastic instrument team. 25 people have worked really hard to bring this instrument to you guys so that you can all do your science with it. And that's really exciting. And they're people, some of which you'll never met, but they've been a fantastic group of people. And so I just wanted to make the science team aware there's a lot of people working behind the scenes to make this happen. And so that's been really exciting, good fun. And I'm looking forward to the next few years. I'll hand back to Scott.
Thank you so much, Julia. Thank you so much, Julia. And thank you so much, Scott. In the interest of time, we sadly can only have one question because we're already running over time. And I'm picking the one from Jeffrey, who's asking for Hector. How much more precise and accurate is Hector actually going to be than the 2DF positioner?
So it does a different role to the 2DF positioner. The 2DF positioner positions single fibers. And that means you have no focus gradient across the fibers. When you put a bundle of fibers, if you position them in the same way, you'll end up with a focus gradient across those fibers. And also the centering of our galaxies is really the key thing there. So it's a different type of positioner with a different key positioning tolerance. But in terms of what has actually been built and machining, it is by far the most precise positioner that we've seen in this sort of context.
Awesome. Thank you so much.